This section we will study about the discrete Fourier transform. We already know the DTFT. We will review and compare between the DTFT and DFT. DTFT defined as this way: the summation and is changing from minus infinity to infinity, and the sequence xn times basis function is e to the minus j omega, and index n is multiplied here. I would like the different color. This is index for n. Okay, this is the DTFT. What about DFT? DFT is defined by, you know that at this moment we measure that we calculate that omega harmonic component of this sequence. In the DFT we are using the kth harmonic, and summation from n starting from number of data is 0 to the number of point n minus 1. So we assume that the data is given n point. This is sequence index n. Data is given n equals 0, 1, 2, 3, like that, and n the final data is n minus 1. So this is n minus 1 data. So we have n data, and we just only take the DFT over here. Then we can converting that one. This is sequence times e to the minus j. At this moment, we measure the frequency spectrum over these separations. So the basis will be given 2 pi over n k. This k means a kth harmonic component, and similarly we multiply the n index. This n index and n is the same. xn and xn is the same. We know that in fact we can assume that the minus infinity to the infinity sequence over here, all the other value of the sequence is 0. Then we can express DTFT with this way: n equals 0 to the n minus 1. Only this is non-zero part. So xn, the basis function is e to the minus j omega, and the sequence is n. Now compare these two transformations. The only difference is this. This one is omega, but here is 2 pi of k. How are we going to interpret that one? Compare here. DTFT cases, we are using the omega as a continuous variable from 0 to the and the pi, 2 pi. But sometimes we can taking minus pi to the pi. It's the same because it's a periodic. So at this moment I just assume that 0 to the, this is pi and comes around the 2 pi. So this is continuous variable between 0 to 2 pi. What about in the DFT? In case of DFT, we select some discrete frequency value. Meaning that if k is 0, then it's a DC component. That's this point. K equals 1, then it is a 2 pi over n. That's this frequency component. And like that, k changing from 0 to the n minus, this one is n minus 1 point. If k is n over 2, k is n over 2, then n over 2 pi times k is, let's assume k is the n over 2 at this point. So k from 0 to the 0, 1, 2, 3, and reach that n over 2, then k is n over 2. Then that becomes the pi. That's the obvious at this point. So from 0 to the n minus 2, n over 2, and coming back to the n minus 1. The last point is this one, n over 2 pi. The maximum k is n minus 1. So this is the maximum value of the k. In that case, the frequency will be given like this way: 2 pi over n, and that is 2 pi minus 2 pi over n. So that means this frequency step is this one. So in the DFT, in the spectral domain is discrete. The step of a spectrum frequency, step of frequency is 2 pi over n. N is the number of sample. So compare between these two things. It's quite similar, but the difference is n. Basically, TFT, we taking from minus infinity to infinity. If we assume that the n is infinity, then this frequency step will continuous. Okay, so when we build up the basis function in the DFT cases, we just assume number of sample is infinity, but among them only n is non-zero. So I said that in the DFT we assume that the data is infinity, but only n sample is non-zero. Okay, that is a DFT. Basically, DFT is not non-periodic. Okay, only data exists over this period of time. All the time is 0. But in the DFT, we concerned only this part. So the frequency steps are given by this way. So we only assume that the n is finite value. But in the DFT, we assume that the data is infinity. It means that n is almost infinity. Then omega becomes continuous. This is continuous variable. So how are we going to converting this one and this one? In the DFT, by adding the 0, that is we call the zero padding. So if we zero padding in the DFT domain, it means that we didn't add any information. The summation range is the same because outside of the n minus 1 is 0. So we don't need to add up here. But if you're increasing that zero padding number, effectively we can increase in this number. So frequency step can be frequency step will be a smaller, narrow like that. If we are using the for example, if we added another n zeros at here in the DFT case, so this point is 2n minus 1 point. We added n zeros over here. Then in the DFT sequence should be summation over here, but the only non-zero on here, so the summation is the same. But in the zero padded cases, we can write down the same spectrum can be estimated. You know that we have to actually take the up to here, but this value is 0, so we added 0 only. So xn and e to the minus j 2 pi over, at this moment we have data length is 2n. So here is n, 0 to the n minus 1, and another n is here. So the total data is 2n. So we are using the 2n times k summary. That's the xk. And the sequence number should be multiplied here. So what's the difference between these two? Okay, it's almost the same except these resolutions. So we changed the number of data, but we didn't add any information. We just added 0. Okay, so just increasing the resolution bandwidth. At this, in these cases, the frequency step is 2 pi over n. But at here, the frequency step is pi over n. So we can finely sample like that. This angle it now becomes the half of this one by adding 0. That's the zero padding techniques. So zero padding just increased the number of samples and the spectrum domain, but the issue is this one. We didn't add any information over here. We just increased the period of this one. We will talk about this one. So at this moment, I would like to let you know that the difference between TFT and DFT. DFT transform and inverse transform are given like this way. I show that in these cases, the the n equal 0 to the n minus 1 is the only non-zero value of this one. But still, we are using the continuous omega. You can assume that we just added the infinity zeros. Then that is obviously equals to this one. Okay. Then the frequency step is continuous in that case. Another important thing is this one. This one is a periodic function. Okay. E to the j omega plus 2 pi should be equal e to the j pi j omega. So this is periodic. So this one is a periodic with 2 pi. But this is not periodic. So this one is the inverse Fourier transform of that. In the sample data, the normalized frequency range is 0 to 2 pi, or sometimes we are taking minus pi over pi. Whatever, it's a 2 pi range, is a normalized one. So that is obtained by real frequency is multiplied by sampling time. So this is defined as normalized frequency. So if signal is band limited in between the Nyquist criteria, then this normalized frequency will confined in this range because this was a periodic. But in the DFT, we are sampled this frequency only these steps. So k times of 2 pi over n. You may think about it, this one seems like a Fourier series. So it's quite similar. DFT is a Fourier series, seems like that. The period is n. Okay, period is n. What's the meaning of this period? Okay, think about that. Frequency step now is this one. And we defined omega n. This is actually W subscript n expressed in this way. So Wn is e to the minus j 2 pi over n. Okay. Okay, you can think about that is the first segment of this one, this part. So, okay, that's the basis of the first the frequency pin. If we taking the DTFT at this time, at this harmonic component, that is this one. Okay, the omega k is this one. Then we can write down that is this definition. What if we're taking inverse DFT? You know that we would like to study of the DFT. So inverse DFT compared to inverse DTFT. In the DTFT 1 over 2 pi, there's a scale factor, and the integration is changing over the index value, and spectral contents is this one, and the basis function is this one, conjugate of this one, and d omega corresponding to this part. Okay, then 2 pi and 2 pi we cancelled out, and then 1 over n summation from 0 to the n minus 1 being harmonic component, and the w of this one should be taking conjugate of this one. The conjugate of this one will become, the sign will change. So this is the inverse DFT. So here it shows that the DFT pair. So by taking the DFT, we need to taking from n equals 0 to the n minus 1, that's the n number of data, and taking summation this one. K means the kth harmonic, and you need to understand that Wn is this basis function. Okay, and the inverse DFT is 1 over n because of this scale factor, and k should be changing from the 0 to the n minus 1. So n harmonic component should be sum up in this way. So we define the DFT and the DTFT. Now compare here that xn n plus 1 should be equal to that one, because if we replace n with n plus 1, you can hear that Wn n will be 1. You can see here the W n over n, nth of this one. This means that just e to the minus j 2 pi over n times n. So this is Wn, and we powered nth power. then this will cancel out. It's 2 pi. So this is 1. So it's a periodic. And x k plus n is also periodic because of this one. So this is periodic function. Then we can reinterpret the DFT. DFT starting data from 0, 1, 2, and all the way down, and last data is n minus 1. We have n samples. This is the sequence axis. So we have n sequence like that, something. But this one should be periodic. It means that we assume that this one starting another, this value is a start here, and 1 and 2 is should be here, and repeated. This one is 2n minus 1. This point is n. From here to here, n data. It's the same as from here to here, n samples. This is also repeated. Minus 1 sample is this one, n minus 1 data. It's this corresponding to this one, and all the way down like that. So even though we are converting only between the 0 to the n minus 1, only we converting only this data, but we assume that this one is periodic because of this function. So we converting periodic function. You need to think about this periodic boundary. This periodic boundary is repeated in these patterns. Even though we didn't intentionally do that, but the DFT natively working in these conditions. That's the preconditions you need to keep in mind. DFT always working in the periodic function. But DTFT, by adding padding infinitely, this is not periodic. So DFT is not periodic function. But in the DFT, basically it's a periodic function in the sequence domain. Spectral domain is also periodic. But in the DTFT, it's a periodic in the spectral domain. But in the sequence domain, it is not basically periodic. Okay. We studied about the DFT. Here shows that the DFT definition is repeated here. Xn is a sum with a basis function of this one. Then it becomes the DFT of the Xn. And the inverse DFT are defined in this way. In inverse cases, we take the conjugate of the basis function like that. And from here, that Wn is this one. So this one just a to j and 2 pi over n. So this is a frequency step. When we take the DFT, here shows that the sequence xn and the number of samples is 0 to the n minus 1 is n sample. So in the spectral frequency step will become 2 pi over n. This is the frequency step in the spectral domain. After taking the DFT, usually it's given like this way, 0 to the 2 pi. So this is 2 pi. This becomes the pi positions. 0 to the n over 2 becomes a pi. That means this is Nyquist frequency. And n position should be equals to this one, 0 position. It's repeated like that. So this part is repeated like that. What about in the negative frequency? In the negative frequency, this corresponds to these positions. And this one will be shown up here. And this one will be shown up like that. So if we using minus pi to the pi, then it looks like this one. This figure is the same as this one. You know that this one is a period from 0 to 2 pi. So that is repeated from minus pi to pi. It should be this kind of shapes. We do this by use of FFT shift. By shifting, this part is repeated over here. Okay, because the DFT or inverse DFT sequence, both of them is a periodic with a period of n. Both of the period is n, because this Wn is a period of n. Okay, it means that n over plus minus n equals to 1. Now consider the delayed version of sequence like this one. DFT by definition is given like this one. By changing of variable, you know that, let me, this one is n prime, then n will be n prime plus n0. So that is replaced to this n value. Then these terms will be comes out, and that is the original, the DFT definition. So in the delayed version, we need to multiply these terms to the original DFT value. The another things at this moment I would like to mention is a discrete cosine transform. Here shows the DFT idea. You know that we have only n data. This is 0, and this end point is n minus 1. But we know that this sequence should be periodic. So even though we only take the sample from 0 to the n minus 1, n sample, number of point is n sample, but basically we assume that that is repeated in this way, n sample like that. So even though we taking only 0 to the n minus 1, but this is assumption, the basic assumption is a periodic one. So this is the periodic signals. But the problem is this one. The signal is not continuous at this periodic boundary. At the periodic boundary, signal is not continuous. So we do not intentionally do that, but if we taking the DFT, it's happen at the periodic boundary. It's not continuous at this point. That will create a large spectral leakage. So that is one of the big problem. To avoid that one, we are using the windowing. So some other name is apodization. So make it continuous in somehow. That is the main topic of windowing. Here shows the window function. We have a lot of window functions exist here. The name is window function, or sometimes we are called the apodization function. Later I would like to explain this one, but the basic idea is tapering out at the periodic boundary with some kind of function. Okay, so one of the simplest one is a triangular one, or some functions like Henning function or Hamming function, Kaiser function like that, Blankman, and this is a flat top window. Like that kind of window can be used to make it continuous at the periodic boundary. But in case of image, it's not that easy. We have certain image cut. So we take the sample from left bound to the right bound like that. But the same image is repeated at here. But this one is not discontinuous. At this boundary, image is not continuous. It's the same top and bottom boundary. At this edge, discontinuity are generated. In case of image, if we apply the window, then this boundary image will be damaged. So to avoid that one, we are using the another techniques. Without using, we can make it by using the mirror image of the signals. We have these signals, but by taking the mirror image, like this one. So if you using this image, then the number of data is increased double. Okay, we are using double one, but this one is repeated like that. So in case of in DCT case, we are taking the number of points is not n but 2n. So 0 to 2n minus 1. But you know that this one is an even function. We are using the complex exponential. Wn is minus j 2 pi over n. This complex exponential has cosine 2 pi over n plus j sine 2 pi over n. But if you look at here, this one is even function, but sine is the other function. If you're taking product between this one, this term will go to 0. We only need cosine terms. So if you are taking DFT by use of cosine terms, that is called DCT, discrete cosine transform. That is one of the way to make it continuous at the periodic boundary. So by taking the mirror image of the signal, we can extend the number of points as double. So, and we only consider the cosine basis, and then we can make a Fourier transform by use of DCT.